So I'll keep it short. I'm going to be showcasing the kind of things I have been doing over my career in numerical methods. I'm stacking the pile initially on geo applications because we are here in Geosolutions, the Australian Geosolutions Corporation. So what we try to do is basically, through computation, allow stakeholders make better decisions. And really, that's what engineering is about, physics is about, and that's the point of what we try to do. So the idea is that we try to formulate problems mathematically, and we abstract the particulars to have a proper formulation that deals with the differences in a way that is constructive, in the way that it structures and uses the framework consistently. So for example, if you want to do flow simulations. So before coming to Australia, I was in a country that rather than bringing rocks out of the ground and selling them as minerals, they would bring liquids out of the ground and sell them as oil. So Saudi Arabia, flow in porous media is extremely important application. Water is also an extremely important application, and they take a lot of the water from the soil too. And basically the problem is that you need to model a reservoir. This is basically a reservoir that has hundreds of kilometers long and hundreds of kilometers deep. And you need to model, this is basically 45 centimeters by 15, I don't remember exactly. And these layers and these lines are basically fractures that determine the flow characteristics. And so you need to be able to quantify effects at the microscale. So for example, this is the same picture, but now looking at the fracture and the structure. So you try to capture the effects of these small fractures in scales that are going to the kilometers. So you have to be able to bridge humongous scales. So basically, that's the multiscale part of the problem. Then you also have processes by which, for example, you start having the position of sand when you're producing oil, or when you have a smog collection in a filter of a car. You have electrostatic fibers that are electrostatically charged, and therefore the particles deposit. And therefore, as the particles deposit, they affect the flow. And as the flow progresses, this clustering starts affecting the flow around it. And as these fibers get loaded by the flow around it, they start forming what they call cake. And the cake starts loading the filter. And then the filter, this is a small block in this pleat. And now you need to be able to model this effect at the pleat scale. And one pleat is not enough to model the whole filter. So bridging all these transfers of information and doing the back and forth of, you have the overall flow that imposes boundary conditions to this problem. And now the boundary conditions change, the flow changes. So you have to readjust what happens here. And then you have to transfer back information. So basically, this is the formulations we built, basically try to transfer this. And then there are things uncertainty in the sense of, now I am in the applied geology department. But basically, what will happen is that geologists will give you distributions of characteristics that the rock will have. And roughly, on average, these things will change every meter, sometimes every foot, sometimes every few meters. And so you will have parameters that define the characteristics of the rock that vary often in the huge scales that you have to model. And so you cannot represent exactly because you don't have enough data about everything. So you have few samples that you took from the whole reservoir, and from there you have to extrapolate. And that extrapolation makes you make different realizations of the same possible, within the same possible constraints, and this induces uncertainty. So a lot of what we do is basically coming up with ways of modeling these processes, writing the proper mathematical description, and then once you have these partial differential equations, solve them, and having the coupling processes between them properly formulated. So this is fairly common in engineering, in the sense of when you have engineered materials. And some aspects of these are also common in geo applications, like reservoir modeling and things like those. But I have found over the years that there's not a lot of cross-breeding, although they're starting to appear over the last 20 years. There has been a lot of venues for people from the two different areas to present results and collaborate. So let me show you a sketch of what we try to do, which is basically a typical process is you have a reservoir that is defined. For example, this is, although the picture is not that good, This is basically a slice of a typical SPE test. SPE is the Society of Petroleum Engineers. So you get this block that is defined by roughly 120 million cells. And you have coefficients that vary in orders of magnitude. So what they're showing here is the log scale. So the different colors represent different orders of magnitude of permeability. And what the operators want to do is want to define how much oil is there and how much we'll be able to recover. And what they want to do that is basically going back and forth between these millions and millions of degrees of freedom is basically very expensive. So what we try to do is basically come up with ways of estimating the effect of the model using model reduction. And that's basically the key of a lot of the contributions we do. So basically, we built infrastructure to be able to model billions of degrees of freedom with hundreds, and give the person who needs to make a decision, the stakeholder, the first digit right. So we basically give you, we can predict the behavior of the fine model up to 1 digit. So we can give you the trend, we can describe the trend, and then what we can measure is that the outputs predicted by these simple models are roughly in the ballpark of the variation of these models. So we cannot give you a number on how this system will work, but with this you can make a decision as an operator. So basically, so to give you an idea, these models take roughly, with our optimized codes and everything, will take about 2 weeks to simulate. But if you are operating in a field, you want to make a decision within the next few hours, should you change the valve or not? And with this, you can make those decisions. And that's basically the goal of what we're trying to do. So I didn't mention it here, but a lot of what we do is solving local problems and finding local ways of representing the solution better. And then we also we treat our numerical method as a black box, and we look at how information comes in and comes out, and we try to parameterize the input-output parameterization. What now is so in vogue as learning, but really it's nonlinear interpolation. So the kind of things we build, and this has been work over 15 years in which I contributed, and 50 years in the community, which is basically you are given this fine detail millions of degrees of freedom problem. You want to come up with 100,000 degrees of freedom that can predict the behavior of this hundreds of millions problem with arbitrary accuracy. You can keep on refining the coarse representation to whatever accuracy you want. And once you have these hundreds of thousands of degrees of freedom, that is something that can run in a few hours, basically a day. And with 1 day, we can start solving in this problem. We do it by solving local problems. We come up with these coarse models. And now, once we have these systems that can run in a day, we can start doing proper thermal decomposition or balanced truncation or whatever method you want for model reduction to control the input and output parameterizations. So to give you an idea of how this works, basically, this model, which is a few 15 layers, if I'm not wrong, of the previous SPE, was reduced to 100,000 degrees of freedom. And then what we were using were 2 global modes with 20 quadrature points. And with these 2 global modes and 20 quadrature points, we can predict the behavior up to 5% error. So we can predict the behavior of this model with only 2 degrees of freedom globally with 20 quadrature points. So basically what we're doing is we're using supercomputing to train a system that then you can run on your phone. That's basically the goal, the spiel of what we're trying to do. Obviously, I'm not here to sell supercomputing. So bottom line is what we do is we want to write frameworks that are agnostic about the details. So this doesn't look like a reservoir. What we do is we put 1 where we have white, 10 to the 7 when we have blue. Although this doesn't look anything like a reservoir, it's much harder to solve than a reservoir problem. It's much simpler to solve the SPE problem that I showed you before than this one. And what we do is we basically have these details. We put a mesh on top of it, which is the lines that you see. And then we solve local problems to approximate the effect of having these inclusions here. Ideally, what you want, I'm telling you the punchline, is that from here, what you would like is to capture these large-scale structures and the little dots to disappear in the background. Somehow, computationally, you have to do that. And the way we have been able to do that is basically by solving eigenvalue problems here. Eigenvalue problems are very, very expensive. And these models tend to have 100 by 100 by 100 degrees of freedom. This is just a local element. So 100 meters by 100 meters by a meter will give you basically 100 by 100 by 100 samples that the geologist gave you for defining the properties of a material. 1,000,000 degrees of freedom, an eigenvalue problem, it's still extremely expensive. So you cannot really solve that. But say we develop technology to actually do that fast and accurately. If you want details, I can show you the papers and we can discuss it. But bottom line is you solve the eigenvalue problem, you get these basis functions, and then you multiply them by traditional finite element basis. And now the multiplication of these times the traditional finite element basis is the thing we write to put into the finite element code. And that object, we can prove that it converges, is stable, and all that. This is the way we go from millions of degrees of freedom to hundreds of thousands of degrees of freedom. The main contribution of all this work that we did was basically, that I was involved, was starting to use ideas from compressed sensing and doing randomized sampling. So what effectively people were doing before we started working on this was basically going to each of the degrees of freedom on the boundary. You have this surface, and putting 1 on each of the degrees of freedom and 0 everywhere else, solve that problem. And solve it and solve it. It's much smaller than solving the global problem because it has only n squared on the surface degrees of freedom, while the volume has n cubed. But what we ended up realizing is that the way cell phones became cheap in the 90s was because people started sending compressed information through randomized sampling. And what we were able to do is basically now, rather than solving a problem for each degree of freedom on the boundary, was to put randomized numbers. Basically, it boils down to defining 1, 0, minus 1, minus 1, minus 1, 0, 0, 1, 0, minus 1, okay? On each of the degrees of freedom on the boundary, and solving 20 problems with that forcing. And those 20 problems, we can give you an estimate of how accurately we represent the problem and the probability by which solving 20 of those problems is enough to represent the problem that you had locally. And this basically became very fast, and we were able to solve these complex problems with arbitrary accuracy. That's what we can prove. Then empirically, what we notice is that if you want 6 bases, it's enough to compute 10 vectors. So 6 plus 4 is enough in mostly all practical problems. We cannot prove that that is the case. The estimates are very bad, much worse than the experience shows. That's the problem with mathematics. Many times you need to have unrealistic constraints to be able to prove things, and then experience shows you that you can do better. So let me skip because I'm going slower than I expected.
No, keep going, as long as you like.
Yeah, but I'm not going to stand between food and beer with pictures, so no, I'm not going to do that. Another thing we do is try to estimate measurements in borehole resistivity using machine learning. And basically, if you have spoken to me about this before, you know that I'm skeptical. So let's not go there, but let me just pose a big picture problem. So a forward problem is, I give you the domain, I want you to solve the problem. I give you the parameters, give me the answer. The solution that you will measure somewhere, okay? The inverse problem is, I give you the measurement that I want you to give me. I give you the volume. Now tell me what was in there, okay? And basically, at the level of abstraction I'm going to discuss is basically this is what you need to understand. So given the subsurface properties and the well trajectory, give me the measurement I should measure. This is the forward part. Then the inversion, inference, learning, however you want to call it, is given the measurements and the trajectory, tell me what was there. And why is this important? Because if you have a layer of rock that you know you have a reservoir there, that you want to extract oil, and you are passing with the well, if you puncture on top, that is, you have this layer, and you cross the top, you broke the seal, and you start losing what you want to extract through the thing you broke. And if you puncture through the bottom, and you cross into water, for example, you start extracting only water, and you stop producing oil. So you don't want to go out of the bound that you're interested in. So we are using basically machine learning. Bottom line, what you need to understand from this is that you need to do some operation at each of the nodes. You have information coming in, you have information going out. Some process at the node has to be nonlinear. You have to do some operation there to cut off, so to decide if something happened or did not happen. Why? Because if all of them were linear, I could collapse the whole network into one node because of commutative properties and for properties of linearity, I could encapsulate all of these into a single node, and therefore you have to do some nonlinear operation somewhere for the network to make sense and not be collapsible. So basically what we want to do is basically have an input from drilling information and do a prediction. How much oil is going to be there, how much water is going to be there. So since at the end of the day, most of what we do is mathematics, what we wanted to do was basically, given that I give you a measurement at a boundary between two different regions, tell me if the measurement I made is as a resistivity 1 up on top, or resistivity 2 at the bottom. Since you cannot distinguish between the drill going this direction or this direction, these two are equally good. What it cannot give you is half of each, because this predicts uniform distribution, okay? We started training networks, getting extraordinarily good results, and they would always fail here and there, here and there, here and there. So we had to start looking at the details as to why were they failing. So obviously what we did is say, okay, fine. Let's train a system to predict square root. Why? Because then I can train it with as many samples I want forever, and I get infinite accuracy. So what we wanted to predict was a parabola. And so basically, this is information I want to predict. This is a forward problem. Now I want to predict the inverse, which is square root. And I'm fine with anything that gives me either the plus or the minus. I don't care. As I said, I don't care if my hand is facing up or facing down. Orientation is not important. What I don't want it to give me is 0, the average. So you give the networks, you train them, but voila, fantastic, no? L2 minimization. You train the network however you want. You minimize the error based on L2 prediction, on the L2 norm. It always gives you 0, because it will be able to predict minus x of the square root of x squared plus x. It averages it, gives you 0. If you will do L1 minimization, you obtain something that is less bad, but is equally terrible. And this is why the method was failing consistently. Because if you pushed it hard enough, you would end up falling here. The methods lack the ability of understanding what you're asking it to do. So the formulation we ended up doing was basically saying, okay, fine. What we'll do is we'll train the forward model. We will train a network to predict the inversion by saying, okay, I have an excellent training system. I want to predict what the network says about the forward model and take the difference of that. Training that gives us this in L2. Training the same way, the forward based on the inversion. So what I'm training here is I am predicting what the model should read on the inverse. And then I plug it on the forward model and verify the difference between, given my inversion, what was the measurement that I report in my network against what you measured physically, okay? So now everything is simple. What's the problem with this? Google, Facebook don't care about physics. They care about social networks, which need trivial computation. Everything is trivial. You compute on a node, doesn't need to communicate. So everything is done on GPUs, single node machines. So we do physics. We need to communicate within the networks. That's why they have these infinite expensive networks to communicate fast, both the data and the data that you want to write and keep, and the communication between the machines. So therefore, we tend to write on other languages and do not use GPUs as often. So what ends up happening is that this model ends up being a finite element code that I write on CPUs. This ends up, the thing inside the eye is a GPU network. And then it becomes just expensive to make the CPU communicate with the GPU to predict. So what we did was to say, okay, fine. What I'll do is two things. I'll train a network to tell me what my forward model says. And then I'll train a network to predict the inverse, as I did before. And now both are networks that can run GPUs. And with this, I basically get extremely robust measurements, and I can do that. And now we can go and do it back on geosteering, which is why the oil companies pay us. No? It's not because they want us to solve the square root. So this is robust, works well. We have a paper on that, and blah, blah. It's robust under noise. And then the next insight is, as I told you before, a lot of the things we do ends up doing eigenvalue problems. So when you do this thing that I am encoding the forward model and decoding the inverse model, you can think of a lot of these networks the same way. You can think of, OK, the compression that happens in image recognition, that's why the machine knows that there's a cat or a dog in a picture, ends up giving you a few parameters to use. And then you have the expansion that gives you basically this picture. You can compress it into that picture. So this part of a network would be the eigenvalue problems we need for multiscale modeling. And we are starting to try to apply that. We had several stumbles at the beginning, but hopefully we'll make some progress on that. So that's the next thing we're trying to do with machine learning, related things. Turbulence modeling and all that, I'm just going to skip. And I'm going to try to show you the new math we're doing. So just bottom line, we have this isogeometric analysis. Is a tool that uses NURBS-based CAD tools, engineering design tools, to describe geometries and solve partial differential equations. So we wrote 2 frameworks, one for scalar problems and one for vector problems that is open source, easy to use, scales from your laptop to 100,000 processors. In 80,000 processors, we got something like 65% scalability, which is fantastic and not so great. So depends on how you see it. Anyway, I'm not going to talk about this other than just throw the idea there. And now I'm going to be talking about what most of my students and everybody who's here from my group basically is working on some version of this thing. So we're doing finite elements where we have adaptive and stable solutions. What does that mean? I give you a problem, simple engineering problem, linear partial differential equation. I put boundary conditions 0, 1, 0 on all the boundary. I try to solve it with conventional methods. I want to find basically this inner layer and the boundary layer on the boundary. Standard finite elements gives me crap. State of the art gives me non-physical solutions. We can do better things mathematically. Either we get smooth solutions by smearing the boundary layer, or we can get these oscillations or a better solution by imposing boundary conditions. Great. But bottom line is I want a method that the user can use reliably without knowing the math underneath, without having the right mesh description. I want the method to be able to tell the user when they have a good representation. So basically, as I showed you before, typical finite elements are these piecewise polynomials. They have the disadvantage that if I give you a wrong mesh, it gives you this or this, which is basically this is 0, 1. This is 5,000. So it's not very physical. The best standard method that you will find in every single framework will give you this. This is 1.5, no? Or negative values. So if you're taking the logarithm of a negative value, the machines don't tend to like that. So a standard mathematical framework is to say, OK, fine. We know that continuous Galerkin doesn't really work. Let's go for this continuous Galerkin, make an explosion of degrees of freedom, and then everything works mathematically. It's extremely expensive. So what we have been trying to do is basically come up with a way of using a mesh, and in the mesh, construct these discontinuous functions and the continuous functions, and take the distance between these two to tell me how well or how bad I'm doing with my solution. That's basically, in a nutshell, what we're doing. And then with that distance, we say, OK, this element needs to be smaller because this is the biggest contributor to my error. I give it to a code, it refines, and then the user just presses enter, leaves, and when they come back, they have a good solution. Better phrased what I just said. So bottom line is we try to solve this problem, trivial problem, linear, advection diffusion equation. 1 in this region, 0 everywhere else. You want the flow to rotate, OK? As I showed you before, standard methods fail. Discontinuous Galerkin will give me a good solution. But the method that we propose basically starts with a coarse mesh that has only three squares with the diagonals. That's the initial mesh. And then by automatic refinement, it can detect where the inner layer is, when the boundary layer is, and all that. In 2 dimensions, great. We can do that the same thing in 3 dimensions. We start with this mesh. The mesh doesn't even reproduce the inflow data. We're putting basically 0. This is pure advection. We're putting 0 boundary conditions there, and a circle that is smaller than the diameter of the element, 1 or 2. 2. And we solve that. We start with this mesh. That's the solution we want, because this is pure advection. Even I can write the analytic solution. It's just a circle that rotates. So this is a mesh that the method produces. This is a solution that the method produces after 30 refinements. Yes, 31. So automatic refinement takes care of itself. Similarly, we can put now diffusion. That is, we put 0 on the outflow. And now we have diffusion, so we have to capture the boundary layer here. We are still struggling to get the right view such that it shows, but basically this is the inflow. This is the outflow, and here has the boundary layer properly captured. And then another thing we can do is say, OK, fine. Most of the time, we don't care about the measurements everywhere. Most of the time, we want to know how well is the prediction in a region, say here. And then we want a method that will give us, for the minimum cost, the solution there. We can basically construct the mathematical framework to do that. And then we can do the following. We can say, OK, fine, let's look at a cube. Obviously, we put it such that this cube, now we put 2 swirls rather than 1. And now the second swirl will only hit it, and the first one won't. If you try to minimize the energy, as I was showing you before, everything is being refined, although, as a user, you only care about the solution there. And we basically can see a method that constructs that automatically on standard open source frameworks. Again, the initial mesh has no information about the problem. And let me stop here, which is the problem we want to solve can be reformulated as this saddle point problem. This is a math. So this ends up being an inner product. The bilinear operator that we want to solve, the partial differential equation that we want to solve, the constraint of this object being orthogonal to the continuous space, jibber jabber. But basically, we want to solve this framework. Is symmetric, positive, definite. Sorry, this block is symmetric, positive, definite. It's indefinite, obviously, because it has a 0 there. We have gotten to the limit of what we can do. Basically, we can solve 10 million degrees of freedom on a laptop, and we obtain the meshes that we showed you. We want to find ways of solving this constraint problem as fast as possible. And now we need to go to parallel computing, and that's where any help you guys could provide us. It's interesting because what ends up happening is that this would be the equivalent of a finite element stabilized method, but this is the inverse of a global matrix. So this is dense. Therefore, this product is dense. So just doing what we have been doing, which is basically just solving it, is not a good strategy. So let me stop here, where I hope for your insights. Thank you.
Thank you very much. We'll have a few questions, but I guess I want to kick off. One of the things that, if you go back to some of your meshes, some of your high-density meshes.
This one?
Yeah. Do you implement any sort of strategy to break up these meshes over threads or anything like that, spectral decomposition or anything like that?
We are using open source frameworks that we didn't write on purpose, because we want to show, actually what we are doing now with 2 of my students is we are just using standard finite element technology, adding a little bit more of information about the jumps of the fluxes at the boundaries. And with that, you don't even need this continuous Galerkin. We can do everything on standard finite element tools. Because at the end of the day, how to phrase it properly? My work has been used by many, many, many people. So I have seen academic impact. But in reality, academic impact is fantastic. I want people to use it outside academia. And for that, it has to be used in tools that people can use. That's why we are using tools that are basically standard. We just implement into someone else's tools. And what we would like to do is basically partner with a finite element company and actually implement this in their codes. At the end of the day, I want users outside academia to just press a button and get a result. That's ideal for me.
So can I interpret that you are trying to go back to engineering again?
That's unlikely in the sense of what I read. Yeah. I was talking to Stuart before that. I'm trying to learn more about physics, so.
Does anyone have any questions?
So I have one. At the beginning, you mentioned you have a massive problem, and I assume you have a massive model as well. And do you use that one to teach the small ones, or?
Yes.
Okay.
But localizing. Let me go this way. No, this way, yes. this way. We do it here. We have, you can think of these details as being the background huge model that you have. And as I mentioned, the coefficient is going to be 1, 10 to the 7. Why that? Because mathematically, although from the outside it's hard to see, if I do 10 to the 7, 1, that's a much harder problem than 1, 10 to the 7. We can go into details as to what. Why is that? But what I want is, you have all these details. The blue are details that I put a mesh, and my mesh knows nothing about. And the only thing I need to be able to do is solve a problem here in this larger block that communicates my element here to the others in a smart way. And effectively, the size of the block I end up choosing has a lot to do with what size I want upstairs. And obviously, what ends up happening is that what we can do, and that's how we solve that's how people dealt with this initially, that is, you end up with a million degrees of freedom eigenvalue problem that is basically impossible to solve. Nobody can solve that fast enough, well enough on an industrial machine. So what they end up doing was realizing that what I can do is solve a smaller box here to see what is important information and extract, say, 2 bases. And then I can solve all smaller boxes and then coalesce those and form another problem upstairs and do a transfer of telescoping scales. We avoided that with the problem I showed before, after, which is basically saying this. You have this underground mesh, this background mesh. And what we do is we solve problems putting 0, 1, and -1 on the boundary 10 times. And I can extract from that the first 4 bases I need to put there. And then we can use error estimates to say how far are we. I mean, we can go into details if you want, but basically the idea is that we can do things that are agnostic about the mesh you want and about the model you want. It's more what can you afford to solve when you want to be online. And it's the same problem as machine learning. Machine learning is extremely expensive, extremely slow, until it's trained. And once it's trained, you can match. So this is the same. Offline, supercomputers need to compute, need to get all these estimates, eigenvalue problems, get proper representations and all that. Once that is done, we can put it on a machine and run on a CPU, a conventional CPU. Because this becomes just a couple of 1,000 degrees of freedom that anything can solve.
Victor,
Yes.
so you're using a smaller problem as an indication of the larger one.
Yes.
So do you have like a sequence of approximations of to how small you take and then you make it a little bit bigger to see if you're converging to something or have an error estimate associated with a convergence sort of study?
Yes and no. For linear problems, yes. For nonlinear problems, which are all the problems that are interesting, no. But what we do is we still have the underlying mesh. So although we compute on these larger elements, we still have the underlying mesh. So we can go every whatever you want, 100 steps, 1,000 steps, 1,000,000 steps, to the fine mesh and compute in the fine mesh the local problem, solve it again, and see the distance between this local representation and what we are saying is a good representation. If that is far, we can recompute, add more bases, and keep computing on the coarse problem. That's effectively what we do. We call that online training, but effectively it's computing residuals. Again, everything boils down to the same ideas. I mean, I think I have 5 ideas that we exchange in different ways, and we combine and have new methods. So.
Anyone else have any questions?
Yes.
So again, connected with the same. One of the problems that we work on in astronomy is basically simulations of the universe, like be a very big scale, so hundreds of millions of galaxies and so on. And of course, you cannot go to the scale of like simulating a single star, right? No. So there is certain simplification on how you model a galaxy, and then you just observe like the evolution of all the galaxies and the statistics. But something that we have is also observations. So for us, we can go very cheap in how we model galaxies, because then we can run many of those and compare against observations and then decide which model fits better in the reality. Is there something similar in this sort of work?
Effectively, yes. The oil companies produce oil, and if your models are not useful, they don't come back to you. That's effectively what happens. They don't give you any data. Actually, the SPE10, this thing I'm telling you that is called SPE10, was an effort from the oil companies to say, okay, fine. None of the oil companies will give you any kind of useful information at all. But they all came together and said, okay, fine. I am interested in having this feature, which is buried somewhere in here. And some other company was interested in having some other feature, which is buried also there. And as a practitioner, the only thing you receive is, this is all the data that we invented because it corresponds to nothing. Model it. And each of them is interested in a piece. And when you simulate, you don't know which piece is to whom, but you can share it. And also what happens is that a lot of my friends are in the companies. So if something doesn't work, I would know, because they would come and complain. And the same way that when someone comes up with a model, I mean, the typical model for fractures is that the whole discussion when you try to fracture a reservoir is, you have these blocks. I can afford to put a square mesh, cubical mesh, and model. And with our methods, you can put the different strata and all that. Now, someone fractures it. So should you model the fracture, the geometrical fracture that you can see, for example, in seismograms? Or should you put what engineers have been doing forever, which is say, OK, I have a block, and I know the fracture goes this way, so my model of the fracture is this block moves here, this block moves here, and this thing approximates the fracture. Obviously, engineers would prefer to have this surface, no? And because it looks better, it's easier to explain to people that there is a fracture and all that. You simulate with a smooth surface and with the steps, with sufficiently good models, with sufficiently well-tuned parameters, you cannot tell them apart. But I can tell you more than one country has invested a ton of money in getting these smooth surfaces from the same company that has the stairs. Depends. If you can sell it, great. If not, you have to have reliable something that is computable. At the end of the day, that's where I stand. Users want to press a button and get a number that they can trust. And we try to provide that as fast as possible. That's basically the motto of everything we do. We want supercomputers to basically validate our models, and then we want to run on phones, ideally. We are not there yet, so I'm not saying that we, but.
It's very interesting, the concept of you use a very big machine and then it costs a lot of money and costs a lot of time and effort. And then once you've expended that effort, you can roll it out quite cheaply and hopefully in a lot of places.
Yeah, because effectively what happens is that even, let's say, oil company, probably the richest in the world, has 3 of the fastest supercomputers in the world. They basically show every few years the billion, have 10 billion, 500 billion degrees of freedom simulations. What is that number? How they decide what is the problem that they will show you is what they can run within a month. But if you're an operation person, it's not useful to run within a month. Operations run much faster, and you need to make many, many decisions. You cannot do one simulation in a month. And that's basically where the bottleneck happens. And that's why a lot of the effort we put is into training the systems to be able to select a cloud of parameters. And effectively, a lot of the things we do is nothing prevents you that once you have a sufficiently good representation of your model here, and you want to have more information about this block, you can put there the original mesh. Nothing in our formulation prevents you from doing that, or for going for a finer mesh. So effectively, a lot of what we do is this telescoping back and forth. And I know I'm way over time, so I can keep talking, but it's not the point.
That's okay. Anyone else got another quick question? If not, we might thank Victor. And as I said, there's beer and pizza outside. If you want to have a look through the data center, grab me. I can take you through. No more questions? Thank you very much, Victor.